So the Copernican insight, it truly most symbolizes this break between the medieval and the modern cosmos. I think it's hard to understate how revolutionary this would be. It took time to catch on, but it was just a radical decentering. But with that decentering also came new choice and responsibility with the human's new place amongst things. So astronomically speaking, the Ptolemaic epicycles had become increasingly cumbersome and incoherent, and it seemed to suggest that there was just some basic fundamental error at the root of the system. The whole thing felt too ad hoc, too elaborate, too whimsical, as the character Orestes said in the Agora film. Copernicus, he believed that reality was Pythagorean, ultimately. And this persuaded him that it must be comprehensible in simple ratio terms, that all of this elaborate epicycles, this couldn't be God's design. So we know historically that the church introduced a calendar reform that Copernicus was brought on to work upon. And so he decides that there needs to be astronomical reform first before we can get the calendar right. So he starts reviewing all the existing theories and data, and he sets to work on the problem of the planets, this problem that's been going on since Plato. This is almost 2,000 years in the works. And Copernicus decides that the only solution is to displace the Earth from the center. He decides that the problem is not the measuring instruments, it's not the method, but it's the underlying geometric model. And so the hope here is that this will end the astronomical errors, that it could end the uncertainties of the age, and save the appearances for Plato 2,000 years later. So I think we're all familiar with the basic idea that the great celestial motions that we see are nothing but a projection of the Earth's own motion in the opposite direction. It's not the heavens that are sweeping around every day, it's us that's turning in the opposite direction. But of course people are going to object, oh gosh, but if the Earth is spinning, that should send objects flying in all directions. But Copernicus counters that actually a stationary Earth would require the heavens themselves to move even faster because they're so far away. So if the entire heavens are moving even faster than that, that would clearly create an even greater disruption. So a nice objection to the classic thought that a moving Earth would disturb everything. So Copernicus's scheme, it had a conceptual elegance to it, which was really important for getting folks on board at first, because when you really got down to the nitty-gritty, I've mentioned this before, at first it actually didn't end up predicting things much better than Ptolemy. And really when you got into it, he even started using epicycles to fine-tune the planets. But what we do know is that Copernicus was influenced by these solar religious narratives and this Neoplatonic sacralization of the sun. We know that he had read Ficino's translations of the Hermetic texts, where the spiritual sun is at the heart of the cosmos. So there seems to be a belief here that heliocentrism could even confirm the intuitions of this magic Hermetic cosmos. That none of this was a metaphor, that this spiritual sun would actually be reflected in the physical structure of the universe. So here's a quote from Copernicus that really paints this for us. Copernicus writes, "In the middle of all sits the sun enthroned in his most beautiful temple. Could we place this luminary in any better position from which he can illuminate the whole at once? He is rightly called the lamp, the mind, the ruler of the universe. Hermes Trismegistus names him the visible God. Sophocles' Electra calls him the all-seeing one. So the sun sits as upon a royal throne, ruling his children, the planets, which circle around him." So it was from it was from reading the astrologer Manilius, we remember, who wrote that early Latin text on astrology, the Astronomica. Copernicus read this, and we think this is the first place that he encountered the idea that the Earth turned on an axis and revolved around the sun. We don't know exactly what Copernicus thought about astrology, but we do have his copy of the Tetrabiblos, Ptolemy's great text on astrology, annotated in Copernicus's own hand, so we know he was certainly familiar with astrology. As I've said before, anybody working in the field of astronomy or mathematics was certainly familiar with astrology at the time. At first, the Copernican system is not taken too seriously in light of the common sense evidence, in light of certain aspects of the astronomy, and not least because of the disturbing implications for religion. Another one of the most common objections was what's called the lack of annual stellar parallax. And what that is if we imagine the sun at the center and the Earth moving around, well, these stars in the backdrop, it seems like when you're on one side of the sun and the other side of the sun, you should see them shift a little bit. But instead, they always seem to be in the exact same place. So people say, that doesn't make any sense. If the Earth was moving, they should move too. The only way this could be the case is if the universe were extremely, extremely large and they were so darn far away that you couldn't notice the stellar parallax. This turns out to be the case, but the proportions involved with how large the universe actually had to be to make the stellar parallax invisible was just so beyond comprehension that people had difficulty believing it. But in any case, Copernicus was a towering mind. He was often compared to Ptolemy as the astronomer of his age, and slowly heliocentrism begins to gain traction, especially with the help of a few others. Let's talk about these folks now. This is Tycho Brahe, Johannes Kepler, and Galileo Galilei. So Tycho creates a system that's a compromise between the Ptolemaic and the Copernican. He has the sun and moon revolving around the Earth, but the rest of the planets revolve around the sun. So the Earth stays stationary at the center, but the planets become heliocentric. Seems like a pretty good compromise. It seemed very plausible. It was generally embraced. It retained all the mathematical advantages of Copernicus without the drawbacks, the physical, cosmological, and theological drawbacks. So this helped to move astronomers slowly towards Copernicanism. In 1572, Tycho observes a supernova. He observes a new star in the sky in the sign of Cassiopeia. He had been a dedicated observer his entire life. He'd been watching the heavens every night, and he knew that that star had not been there before. And suddenly it came on the scene, and it was as bright as Venus. It was just astoundingly bright. For 2 weeks, it could even be seen in the sky at midday. Then over the course of the next 16 months, it changes colors and then fades out. Tycho watches it, he measures it, and he notices that it doesn't move against the starry backdrop. And so it must be very far away, for the same reasons we were just talking about with stellar parallax. This new star could not be beneath the moon. It couldn't be in the sublunary sphere. And if you remember from Aristotle, this is where all imperfect phenomena were said to happen. The heavens were perfect, and it was just the sublunar realm that was subject to change. So this was empirical evidence that defied the Aristotelian cosmos. This was previously considered impossible. So the implications here are huge. They're as pivotal as those of Darwin and Einstein. They're saying that change happens in the immutable heavens. It's breaking down the celestial-terrestrial divide. Tycho was famous for his pursuit of astronomical accuracy. There was a Jupiter-Saturn conjunction in 1574 that was said to cause an outbreak of the plague, and he noticed that the Alphonsine tables, which he had inherited from Ptolemy, which were the standard, they were off by a month in saying where the Jupiter-Saturn was going to be. And even Copernicus's most recent data was off by a few days. So he was really driven. We need to get the accuracy right. We need to get this data and these numbers right. So in 1576, he began the construction of Uraniborg, and that was a huge observatory that he built on an island near Copenhagen. His patron, who was one of the royalty there, gave him this island, said, yeah, go to town. You know, this is a little bit like Ficino's situation, but he was given a whole team. They constructed all these new instruments, and he began a 20-year program of just making the most precise measurements that had ever been made astronomically. He was able to, when he really wanted to, he could make observations within 1 minute of arc. This is before the telescope. 1 minute of arc, we're talking 1/60th of a degree. He was the best naked eye astronomer in history by far. And his data that he collected here, you know, much in the vein of the astronomical diaries in a way, would be pivotal for moving Copernicanism forward. As we will see, Tycho's student was Kepler. He saw Kepler, he took him under his wing, gave him a job, and he sets Kepler to work on problems involving Mars's orbit. And this ends up being really important because only Mars has an orbit that's elliptical enough to have an effect on its observed motion. Mars had always presented a particular problem for the Platonists. This is kind of ironic because Mars is the nocturnal malefic planet, posing a problem with its elliptical orbit. And so by this kind of wonderful happen chance of history, the 20 years worth of data that Tycho had compiled were entrusted to the one person who was capable of figuring them out and construing them correctly. Tycho was not able to extract a working theory from the data. But it had to be Tycho's data because the previous data, it was so imprecise that it actually could have been explained by circles. So you had to have Tycho's data and you had to have Kepler's mind to be able to make this breakthrough. In 1609, Kepler he publishes the Astronomia Nova. This contains his first 2 laws of planetary motion. It shows that planets move in ellipses, sweeping out equal areas over equal times. We'll look at this more in a minute. But this is really the death blow to any hope of an Earth-centered cosmos or to circular motion in the heavens. Just changes the face of astronomy, kicks off the modern era, really. So finally, at long last, the empirical data and the abstract mathematical reasoning mesh perfectly, just unlike ever seen before. This is really the crowning of this project that was started by the Assyrians in the astronomical diaries, the empirical project, but it's also heir to the ideal model building tradition, and it brings them both together in this most perfect conjunctio, this sacred marriage of data and model. Epicycles are no longer needed. This saves not only the appearances, but it shows how mathematics is truly the language of nature, and it's like a total fulfillment of the Pythagorean worldview. A little later, by 1627, the Rudolphine tables are published. These are based on the 20 years of Tycho's painstaking data and 10 years of Kepler's theoretical work. These are the best tables yet by far, and they become the standard for the next 100 years. Let's talk a little closer here. So these are showing the different geocentric and heliocentric models. So here we see Ptolemy, of course, with the Earth at the center, surrounded by the spheres of the Moon, Mercury, Venus, Sun, Mars, Jupiter, Saturn, as we know. Aristarchus's heliocentric model, way back when in 300-some BCE, and Copernicus's both look like this. They've got the Sun at the middle, surrounded by circular orbits of Mercury and Venus, Earth, the Moon orbiting Earth, etc., as we know. Tycho's model, so you can get a visual of it, is over here. So you can see that the Earth is still at the center, stationary, in the big circle, but the Sun is moving around the Earth on this ring, and then all the other planets are centered upon the Sun. Mercury and Venus first here, and then the superior planets. So this whole clockwork thing is moving around. So everything is heliocentric except the Earth. This is the compromised system. But one of the ways that this starts to inch people towards Copernicanism, just to give an example, is, as you can see here, the orbit of the Sun intersects the orbit of Mars. So to get the data right, this was necessary. But the implications of this is that it can't be the crystalline sphere model that everyone used to think. They'd say, oh, the planets are embedded in these crystalline spheres, the spheres are circling. But if these crystalline spheres have to intersect one another, well, that kind of notion of there being spheres goes out the window. So it's little bits like this that inch people closer to Copernicanism. This is another model that was actually developed even before Aristarchus, slightly before him, which places the Earth at the center and the superiors around the Earth, but then only Mercury and Venus are circling the Sun, which seems pretty plausible. If you think about the visual way that Mercury and Venus don't get very far away from the Sun, you could, of course, think that they were centered upon the Sun. So it's another possible compromise model. And then finally, we see Kepler's universe down here. No more circles. These are ellipses. Sometimes the ellipses are pitched towards one another. A totally different universe than conceived before. So let's talk just a little closer about Kepler's 3 laws of planetary motion. The first law is just that planets move in elliptical orbits. They move in ellipses. And over here we see how an ellipse is defined. If you watched the Agora movie, you might remember they have that cone that she takes apart, and you can see that an ellipse is a sort of pitched circle. That if it was absolutely flat, it would just be a regular circle. So a circle is a special case of an ellipse, but as it gets more pitched, we see these more classic ovals. Part of that law is that the Sun occupies one of the foci of the ellipse. It was also shown in the movie how one way that you could draw an ellipse is if you imagine a string stretching here between A and B. That string is going to stay the same length. If I have a post here, imagine this string is attached to 2 posts, and then I've got a pencil right here, and I just roll the pencil as far as the string allows me to. As B gets shorter, A will get longer, but the length of A and B will always stay the same. And that is one way that you can define the elliptical orbit. The second law says that as they move, planets sweep out equal areas in equal times. So if we look over this diagram, in the time that the planet moves from P to P prime, it's going to sweep out this much area. So if it is moving, if it's going to sweep out that much area when it's this close, each of these are equal areas, it's going to have to move a lot faster when it's over here. So when it's on the left side, to get from P to P prime, it has to cover more distance. So it's going to move faster over here, but when it's further away from the Sun, it's going to move slower, so that the hashed area is equal in each case. Moving slower when it's further away from the Sun, and then speeding up so it can cover the same area when it's closer to the Sun. So this was also a big change. They had always thought that the planets moved at a uniform rate around the circle. Now they're suddenly slowing down and speeding up as they move around the ellipse. This diagram here shows an early version of the second law. Just want to illustrate here how there's a Neoplatonic intuition going on. At first, Kepler thought that there was an inverse relationship between the distance and the speed of the planet, so that when it was close to the Sun, it'd be moving fast, and when it's further away, it'd be moving slow. And he thought that was because the Sun was shooting out these visual rays. If you remember these rays we talked about with Al-Kindi, the Arab philosopher, and that when it's farther away, there's less rays hitting it. You see how there's fewer rays hitting P here, but when it gets close, there's all these rays hitting it. So he thought that all those rays hitting it made it go fast when it was close and slow when it was further away. This is not the case, physically speaking, in terms of how the physics works. Later they learn about gravity. but it was this intuition about the sun's role and the way that the sun was moving everything around it, that it was the conductor of the dance, so to speak, that led him to these breakthroughs. So we want to see how the solar religious narrative actually leads to the scientific insight. It's a belief in something archetypal that makes the scientific breakthrough. It's not just number crunching. Similarly with the third law says that there's a proportional relationship between the period, the orbital period, how long it takes to go around, and the size of the semi-major axis, this little part here between one of the foci and the edge. This doesn't actually provide any new information, but it's one of those things that's like really cool. It's kind of like the golden ratio showing up in all these places. Kepler was really excited about this law because he felt like it showed the Neo-Pythagorean regularity of God's cosmos. And it was these kind of Pythagorean Platonic insights that were driving the whole process for him. So in 1609, he publishes the Astronomia Nova, which has those first two laws of planetary motion. And then in 1610, Galileo, this groundbreaking publishing of the Starry Messenger, the Sidereus Nuncius, he publishes this observational evidence from his telescope, which we'll look at now. And some people say that, this is as good a date as any to mark the beginning of the modern era. Within 2 years, the problem of the planets is solved, and then all this empirical evidence supporting the Copernican system comes through the telescope. So let's look at that data. So the first two things, craters on the moon and sunspots moving. So Galileo turns his telescope towards the heavens. He didn't invent the telescope, but he was one of the first to turn it upwards, and certainly popularized its use astronomically. And he discovered that the moon was covered in mountains and craters, that it was imperfect. And so the idea is that, okay, no, the Earth is kind of like the moon then. Again, breaking down the celestial-terrestrial divide. Copernicus could be right if both the Earth and the moon are kind of in the same category, and they're both imperfect and changeable. Galileo even uses the length of shadows that he sees through his telescope at times when he knows exactly the position of the sun, moon, and the Earth, so that he can actually make a moon topography, which turns out to be very much like the Earth's topography. It's got mountains and valleys. Likewise, with sunspots, he discovers that on the sun there are these imperfect spots, and not only are they there, but they're moving. And this suggests that the sun itself is rotating. So this suggests that this is a changeable heavens. It's not an unchangeable heavens and a changeable Earth. It's changeable all the way up and down. And so this would really support an Earth that moves if there is a heavens that move as well. First two pieces of data. Next two, the moons of Jupiter and the phases of Venus. So these are, if you're looking through a telescope at Jupiter on 3 different nights, you might see 3 little pictures like this. This is Jupiter with its moons kind of moving around. And at first you would say, what's going on here? In this bigger picture, it shows us on 9 consecutive nights the position of the different moons of Jupiter. So let's look at Io, this black dot, for a second, and I'll follow it down here. It's here, and then it's here, and then it's here, and then it's here. And you can see that every 2 days it changes which side it's on. If we look at Europa, it starts over here, it moves over, and then it moves back, and then again, but over a slightly longer period. It's not every 2 days, it's every 4 days. Ganymede, likewise, takes an even longer period. And Callisto, the longest, starting over here, and in 9 days only making a half a cycle. And so it turns out that the easiest explanation for the changing location of these points is that they are orbiting around Jupiter, and that the wider orbits that are further out take longer to go around. They take longer to move back and forth across this diagram, whereas the ones that are close in, they're going around real quick. And so this gives credence to the Earth-Moon system. It says, oh, okay, so that's going on with Jupiter. Maybe the same thing is going on with the Earth. And it actually gives us a visible model of Copernicanism itself. Jupiter with its moons is like a little mini test tube version of the whole solar system. Solar system has the sun at the center with the planets moving around it. Jupiter is at the center of its system with its 4 moons moving around it. So it allows astronomers to see it and to start to imagine it. The phases from Venus. This was a really powerful one because Copernicus actually predicted ahead of time that this would be the case, and that if we could see it, then that would prove his system. This is a little bit like Einstein predicts in advance that general relativity could be proved by doing a certain experiment with an eclipse and kind of measuring something that happens on the edge of the eclipse. And they famously did that eclipse experiment, and it proved general relativity right. Likewise, this is what Copernicus says about the phases of Venus. So if we're in a Ptolemaic system, this is what should happen with the phases of Venus. The Earth is here at the center, and as Venus rotates, when you see it, if you're looking from Earth and seeing Venus in relationship to the Sun, you're going to see crescents all the while that Venus rotates around the Earth. You're never going to see a full Venus because you're never going to get the viewpoint of Venus being fully lit up. You could see Venus will disappear when she passes in front of the Sun, but you'll never see her full face illuminated. Whereas in the Copernican system, as Venus emerges here from lying hidden, she'll be a crescent, and as she comes around, she will begin to wax. You'll be able to see more and more of her until when she almost disappears behind the Sun, you'll almost be able to see her full. And so here the phases go from crescent to nearly full, she disappears behind the Sun, emerges nearly full, and turns to crescent again. Whereas in the Ptolemaic system, it would have been only crescents all along. You would never get this full phase. And so indeed, this is what Galileo sees through the telescope, proving that Venus is circling around the Sun, not circling around Earth. Further evidence, the stars in the Milky Way. The Milky Way, when you look up, it looks milky. It looks like a kind of smudge, but when you look at it through a telescope, it resolves into points of light, into actual stars. This suggested that, okay, these were stars like the ones we could see, but they were just so far away that they became this kind of milky blur. And so this was evidence that, no, the universe is that huge size that people doubted it to be. And so some of the stars are so far away that they become a Milky Way smudge. Similarly, when you look through a telescope, the Sun gets bigger. When you look through a telescope, the Moon gets bigger. When you look through a telescope at Saturn, it gets bigger, and suddenly you can see the rings of Saturn. But the stars, they don't get any bigger. They still just look like points of light. And that's because they're so far away that you're not noticing the tiny little bit that they're magnified by your telescope. It's the same reason you don't see the annual stellar parallax. They're so far away that they continue to just look like a dot. And so this explains why you don't see the annual stellar parallax. It's empirical evidence that that's what's going on, that those stars are so far away that they're not being increased by the size of the telescope. So what this all amounts to, eventually Kepler's laws and his tables would have convinced all astronomers. They were accurate enough, but they were mathematical and they were abstruse. What the telescope did is it had the power of convincing the layperson in an accessible and a non-mathematical way. Anybody could look through a telescope and see for themselves that actually the world didn't conform to naive common sense. It didn't do the things that you thought it was going to do. And many people did get telescopes and start looking up towards the sky. Galileo popularized astronomy, and the astronomy that he popularized was a Copernican astronomy. So this was pivotal for Copernicanism being adopted and accepted as quickly as it was. He was really evangelical for the new cosmology, but eventually Galileo ran afoul of the church. All right, let's talk a little bit just about the religious reaction to the Copernican Revolution as we wrap up here. So Copernicus himself had been well connected to the church. Different powerful church people had supported the publication of his manuscript, which he saw published the same year that he died. He got to see a copy of it on his deathbed. Good for Copernicus. But eventually, political motivations are going to cause the church to oppose Copernicanism. In a different time, the church would have adapted different conflicts with Scripture through metaphorical readings. This is what the scholastics were doing with the new science that was emerging out of Aristotle. But a lot because of the Reformation, because of the Lutheran emphasis on the literalism of Scripture, it pushed the Catholics in their counter-Reformation towards a similar literalism. So they ended up coming back strong against Copernicanism, trying to squash it as a threat to their power, really. Because it had upended both the religious cosmos of Dante and Aristotle, but also the political power structure of medieval life, because it displaces the centrality of humanity and the Christ event. It's no longer the center of God's plan. So just like the Reformation was a threat to the church, so Copernicanism became a threat to the church. In 1600, this Neoplatonist named Giordano Bruno is burned at the stake by the Inquisition for his Neoplatonic views about infinite universes he wrote about, what today we might call the multiverse. And in 1616, the church declares the Copernican theory false and erroneous, despite its popularity in many circles. And then finally, in 1633, an aged Galileo is branded as a heretic. He's forced to recant his views, and he is placed under house arrest for the rest of his life by the Catholic Church. All of this had really weighty consequences for the church. Ultimately, it undercut the church's legitimacy. They doubled down on this religion over science thing, but it really ended up being a losing move for them. Because the Copernican Revolution would succeed, and it had only kicked off an even bigger scientific revolution, which would in many ways demolish both Christianity and astrology, as we will see next week. So despite this real unfortunate political gamble on the church's part, formerly Catholicism had always been more hospitable to astrology, more hospitable to magic, because of the rituals of the church. The rituals of the church were already these kind of like white magic acts. Things like the transubstantiation, transforming the bread and wine into the blood and body of Christ. This was a miracle that was performed every Mass. But wherever the Protestants held sway, they thought these rituals were ridiculous. Protestants don't believe that the bread and the wine are actually transformed into the body and blood of Christ. They say, no, this is just a metaphor. They ridicule these things as hocus pocus. This is, the word hocus pocus actually comes from a slurred mocking of the sacramental words in Latin, hoc est corpus, meaning this is my body. Hoc est corpus became hocus pocus in the mouth of the Protestants, ridiculing the Catholics. So you can see the Protestants, by contrast, regarded any kind of magic as diabolical. But in just a final showing of this hypocritical world of the church, I wanted to read this early 17th century description of astrological magic being used behind the scenes in the Vatican to ward off evil omens that were portending the Pope's death. So at the same time, that Galileo's under house arrest, this is going on. And this same Pope, he had just condemned astrology and banned the publishing of astrological works. And meanwhile, he's bringing in the astrologers to ward off his own death through astrological magic. Of course, this isn't any more hypocritical than the Roman emperors who thought that astrology was just too dangerous to be practiced by the common people, so they outlawed it, and they practiced it themselves. So listen to this quote. It's kind of a cool look behind the scenes in the Vatican with astrological magic being used. First, they sealed the room against the outside air, sprinkled it with rose vinegar and other aromatic substances, and burnt laurel, myrtle, rosemary, and cypress. They hung the room with white silken cloths and decorated it with branches. Then 2 candles and 5 torches were lit, representing the 7 planets, since the heavens, owing to the eclipse, were defective. The other persons present had horoscopes immune to the evil eclipse. There was jovial and venereal music of Jupiter and Venus, which was to disperse the pernicious qualities of the eclipse-infected air, and by symbolizing good planets, to expel the influences of bad ones. For the same reason, they used stones, plant colors, and odors belonging to the good planets, Jupiter and Venus. They drank astrologically distilled liquors. So just to give you a feeling, it's like, wow, this sounds like a scene out of Ficino's villa, but it's happening in the Pope's quarters at the Vatican. And meanwhile, they're burning people at the stake for believing this stuff. It's ridiculous. Don't mean to end on such a negative note, but it's just to see the wide variety of where astrology is showing up, how it's showing up, the different contradictions and power plays involved. But we've just clearly seen astrology has come back to the very center of cultural life, to the very highest reaches of power. From where we were in the early Middle Ages, when astrology was pretty much dead and not practiced, it has made a full resurgence, a full revival. It will meet some trouble next week in the face of the scientific revolution, but that's for next week. And cheers to the sun.